that's a transformer core. And what are these lines?
Laminations.
Laminations, what for?
Prevent any
To reduce eddy currents, because eddy currents eventually will produce a lot of heating effect, and therefore you're losing energy. So, and that comes as heat in the core, and that not only loses the energy but also kind of heats up the coil, which can spoil the insulations and stuff like that too, and then finally it can short circuit. So we have primary windings connected to an alternating source. So Vp is the input voltage, and then we have a secondary that will have a voltage Vs. Both are back EMFs, so I have done those things in detail, so you should be familiar with this. So what we ended up doing is this equation. Vp over Vs is equal to Np over Ns. Np is the number of turns in the primary, and Ns is the number of turns in the secondary. So we have this, and this is basically what we call as the voltage ratio equal to turns ratio. Voltage ratio is equal to the turns ratio. Okay? Like for instance, you have 120 volts over there on the wall, but suppose you need a transformer to use it for smaller purposes, and let's say we have 20,000, let's say 20,000 turns over here, and 1,000 turns on this side. So how many volts can you get there? So all you do is use this equation. You're putting in 120. Vs is what? Is equal to Np, 20,000 turns over 1,000 turns. So Vs is equal to 6 volts. So you get 6 volts as the output, and it will be alternating. That's also going to be alternating, and that is 6 volts over here. And this is called a step-down transformer. I mentioned that to you, right? If Vs is less than, if Ns is less than Np, if Ns is less than Np, then Vs is less than Vp, and that's what we call as step-down transformer. I'll define the word transformer later on. And if Ns is greater than Np, then you have Vs greater than Vp, and that is called a step-up transformer. So step-up transformers and step-down transformers are the two kinds. And there's a third kind which is not supposed to be used. I mean, like the third kind is it's called an impedance matching transformer, which we don't normally cover here. So don't worry about that part of it. You just have to worry about, not worry, you just have to know about step down and step up transformers. So if we just take, for example, a television. The television, there are parts in the television which require an operating voltage of 400 volts. And there are parts that are requiring only 3 volts. Some require 20 volts. Different sections of different boards, different sections of the boards will operate on different voltages. So you need to provide all those things. So all you have is 120 volts. And 120 volts AC goes to the transformer, and then once it goes to the transformer, it actually can be stepped down or stepped up. That's why you have all these multiple leads, you know. So you can actually have 2 volts, 5 volts, 9 volts, 12 volts, 20 volts. They're all here, depending upon the purpose. Like what's the use, what's the circuit that you have, and what's the transformer that needs to be built to provide power for that one. That is why we have transformers. doing the job of stepping up or stepping down. Now, the CRT televisions, the big ones, the picture tube runs on somewhere between 10,000 and 20,000 volts DC. So, because you need to accelerate those electrons to the screen, and that's also provided from here. How do you get 20,000 volts from there? Step up. So the step up transformer is what is used inside the television to provide the necessary 20,000. But then there are many parts of the same television which requires only smaller operating voltages. So we have transformers of all kinds. Like even looking at this power unit. If you look at this power unit, you have all of them are DCs. Can you see red, positive, black, negative? They're all DC. But what goes in is 120 AC. 120 AC is getting stepped up to 200 volts, then 150, then 100, then 50, then 5, and then 6 and 1.5. The bottom one is 1.5 volts. But they're all coming from there. So the transformer, this is heavy because of the transformer. Okay, so the transformer is the one which actually steps up or steps down to get it there. And of course, after the transforming action, what you have is still AC. This is still AC. And then you need to rectify it and then make it DC. I think I mentioned about rectification earlier, right? Using what? What component? Diodes. We use diodes, at least 4 of them, to rectify this AC into DC, and then we use capacitors to smoothen it out. Any questions about it so far? Everything's okay? Now let's talk about current. The current over here, called the IP. The current is IP over here. Now that IP, if the secondary is not connected to anything at all, if the secondary is not connected to anything at all, this IP will be nearly 0. And the reason is because when you push 120 into this transformer, what gets kicked back, there's a back EMF, that is nearly 119.99 or whatever. That is what comes back. So the net voltage is very small. It is significantly nothing. And therefore, the current over here will be hardly anything. Okay. Now, why it is not 120 returned and it's only 119.99 is because of the efficiency of this whole thing. You know, the flux is dB over dt, the continuously changing magnetic fields inside. The continuously changing magnetic fields inside that can leak a little bit. A tiny bit of leakage is possible. And then eddy current, you can't remove it completely. So there is still some eddy current which is going to oppose you. So it opposes all this. And because of all these reasons, you won't get it 100% back. You always will have something less. Get it? A little bit less. So the voltage is like 119.99. And there's nothing here. What happens when we connect this output to, say, a light bulb? If you connect it to a light bulb, then what happens? Let's say the light bulb's resistance is 6 ohms. If the light bulb's resistance is 6 ohms, how much current will flow there? What is IS? 1 ampere, right? 6 volts, 6 ohms. So 1 ampere. So you can get 1 ampere in the secondary lighting up the light bulb. The light bulb was specified to work on 6 volts, so this light bulb glows. And it draws 1 ampere. Now what do you call this current? Yeah, secondary current, but what is it? Induced current. And according to Lenz's law, induced current flows in which direction? In a direction to oppose the cause. What causes this? This. correct? dB over dt is the main cause of this. So this current is going to flow in what direction? It's going to flow in such a way to reduce this, to kill it. And therefore, dB over dt will be lesser. The dB over dt will be affected because there's a current flowing now. And when dB over dt is affected, remember the dB over dt is common for both primary and secondary. So what happens to the back EMF here? The back EMF in the primary is minus d phi over dt. What happens when the dB over dt is affected? The back EMF will be higher or lower? Lower, because when the dB over dt is dropped, d phi over dt is also dropped, and so you won't get too much back EMF. You may get, say, 119. You may get 119, but not 119.99 like before. Why? Because when this current flows in such a way to oppose the cost producing it, and the cost is dB over dt, and the dB over dt therefore drops. When the dB over dt drops, the EP drops. When the EP drops, the net voltage is higher than before. Before it was like 0.01 volts, now it is 1 volt. And if this is 1 volt over here, and if this coil has some resistance, then definitely an IP is going to flow, right? There will be a primary current going here. There will be a current here, because now this thing has increased. So the more and more you draw from here, it's going to ultimately come from here. Make sense? Although there is no electrical link, no electrical connection, but it works. So when you start drawing more and more current over there, the more and more current will be flowing here. And that more and more current flowing here is drawn from your source. So it's kind of indirect drawing. You draw from the secondary, but the current is pulled out from the primary. Now when you short the secondary, this current can be higher, which means this will be dropped a lot, and then this current can go really high. And when this current goes really high, it burns up the coil. So by mistake, if someone shorts the transformer's secondary, nothing much happens in the secondary. It's a primary that gets affected. It burns off. So if the transformer fails, it's mainly the primary that's, it depends on what transformer you're talking about. But right now, you understood this situation? Now. So, when you supply Vp into the transformer, it draws Ip as a current. And on this side, we have a Vs and an Is. So if you look at it one way, energy is used on this side, but where is it going to ultimately come? From this side. So the energy input should be equal to the energy output. Is that right? The energy input should be equal to the energy output. Law of conservation of energy. And this is only true for an ideal transformer. What's an ideal transformer? Yeah. Ideal means what? 100% efficiency. Efficiency 100% means what? There's no loss. So if 1000 joules go in, 1000 joules come out.
And then does this only not work because
that doesn't work always. So ideal transformers are difficult to achieve. You can get nearly ideal, but never 100%. Why not 100%? Reasons.
heat,
Say it again.
heat,
From the heat. Where is the heat coming from?
eddy,
Eddy current. Now, the heat coming out from the eddy current is called iron loss. You know why they use the term iron? Because eddy currents are formed in the iron. You get it? So it is not that it is losing iron. So there are many reasons why something cannot be ideal. The main reasons are magnetic leakages, magnetic loss, Magnetic loss is something that is possible because it's, you cannot contain everything into the core all the time. There are leakages possible. So magnetic loss is one of them. Ion loss, which is basically the heat from the eddy currents. Ion loss is the heat from the eddy currents. And then the other kind of loss is the copper loss. Again, this is not losing copper. What is that? What is lost? Heat in the copper wires. Because you are having a current flowing through copper wires. Copper wires do have some resistance, right? So there is definitely an I square R heating effect that's going to take place in. So this is a heat from the currents in copper wires. Okay. So the copper loss is the heat from the currents in the copper wires. Iron loss is the heat from the eddy currents, and the magnetic losses. All these are responsible for if a transformer is not ideal. So for ideal transformers, none of this should exist. So that's why it's difficult to achieve 100%. But yes, some transformers are literally pretty close to 100%. I mean, this one should be a good quality one. It can be really good. So that means no form of energy. I mean, this will lose a little bit of this, so you can't avoid it completely. But instead of being 100%, maybe it's 99.5% efficient. That's good enough. Efficiency. Okay? So now, energy input is equal to energy output. What's the formula for energy? Energy, power times time. Power times time is energy. So power input times time is equal to power output times time. Right? Which means power input should be equal to the power output. Power input should be equal to the power output. What is the formula for power? Electrical power. VI. So it's going to be VP IP is equal to VS IS. VP times IP is a power is equal to VS IS. Now if I want to get the ratio of VP to VS from this, what do you have? IS to IP. So you can see that the voltage ratio is the reciprocal of the current ratio. The currents get... So if you're talking about a step down transformer, what do you think is the current? Step up. The current actually steps up. That means you will get more current here. Okay, the voltage is less, but the current should be higher. So if the current is 1 ampere here, the current should be smaller on this side. It should be smaller. So use this equation and find out how much is the current in the primary. Go ahead. VP over VS, 120 over VS, 6, that you already found out, is equal to IS, which is 1 over IP. So what is IP? 1 over 20, which is 0.05 amperes. So even though the current is 1 ampere on that side, it is going to be 0.005 amperes on this side, on the primary side. So you are drawing a current for charging something, and you're drawing 1 ampere on this side. But see how much current is drawn on this side. It's only 0.05 amperes. It's small. Now, if you don't connect anything on this side, here, if you don't connect anything at all, like a light bulb, if you leave it open, then the IP is going to be negligible. So the power consumed is also negligible. So you don't have to really pay for anything in terms of electricity. That's why we plug in so many things and we don't even care about it. Right? The printer is already plugged in. television is plugged in. It's ready. All you need to do is push the remote and the TV comes on, right? So it's waiting for the signal to turn on the power to the transformers and to all the circuit parts. That's basically what it is doing right now. It is in a standby mode. But is power going to the transformers inside already? Power is going into the transformers, but it is not being used. The transformers are power ready, but nothing is coming out from there. Nothing is being used from there. And that's the reason why it is not going to consume any electricity. It is consuming electricity. Maybe if I'm looking at the television alone, you may have to spend a cent maybe for after a year. So it's not something that we have to worry about, you know. It is a tiny bit. And that tiny bit, if at all you're paying something for that, it is for the convenience. How many of you like to, like unplug the TV after you're done? You want to unplug it and then go home. Come back again, plug it in. So then, of course, you're losing the convenience of turning it on with the remote control, right? So, so the current in the primary is going to be smaller because it's so step down transformer, IS is greater than IP. Step up transformer, IS is less than IP. So when you step up the voltage, the current gets stepped down. Okay? And vice versa. So that's about the power. All right, now what is the definition of a transformer? Write down the definition of a transformer, just in case you like to keep it. All right, transformer. It's a device that transforms or transfers electrical power from one electrical circuit to another electrical circuit. From one electrical circuit to another electrical circuit. Without an electrical contact. Without an electrical contact. Okay? That is basically a transformer's main job. But yes, electrically there's no contact, but there's a magnetic contact. There's always a magnetic contact, not electrical. So your phone charges, when you're keeping the phone next to it, it is transforming electrical power from one side to the other side. Again, when you don't put the phone over there, that setup that you're plugged in already is not going to do anything. There's no energy loss, right? Only when you put the phone over there, it will start working properly. The reason is, as soon as you put the phone there, you're producing induced current to charge your phone, so then this current will start flowing. So this will not start unless you use it. Okay? Now let's see how these transformers are beneficial in certain cases. Any questions on this? High tension transmission. High tension transmission. The word tension over here in fact refers to voltage. Voltage. It's not like tension as in tight. High tension. The word tension in this case is high voltage. So high voltage transmission. And how the high voltage transmission is beneficial is what I'm trying to show you. So let's say Where do you get electricity here? Where is it produced? Come on. Yeah, but that's not produced there, but where is it produced? Like, where is the plant? LG&E. So the electrical power plant. So what they do, they actually burn coal. Here they burn coal, and then they use that coal to produce heat, and the heat is used to change water to steam, and the steam is made to turn this turbine, and the turbine is connected to the generator, so the generator starts spinning like that. The generator starts spinning because the turbine is making it spin, and when the generator starts spinning, it produces electrical power. And that electrical power has to be distributed. The problem comes in distribution. Production, okay, this is one area. Distribution, how to send it to everywhere. And what is needed. In fact, electricity is the best form of energy that can be transported from one place to another place without much loss. There's no other energy form that can be transported from one location to another location without much loss. Okay? Electricity is one. The best, in fact. Electricity is the best. If you want to pass energy from here to a village which is like 50 miles away, yeah, you can actually send electricity from here to there without hardly suffering a loss. Whereas think of any other form of energy. Heat energy, sound energy, any sort of energy, it's not going to work. You will end up losing it on the way. So, so let's look at the scenario where, okay, again, this room, how many amperes is it drawing right now? Probably around 10 amperes, just by the lights and stuff like that. If 10 amperes is drawn just by this room, look at all the rooms, look at all the current that is supposed to be coming into Trinity. That must be a lot. The current that's entering Trinity's wires is going to be high amount, huge. If you go and find out where the actual wires are bringing electricity to Trinity, look, it's that big. Because it has to send that many amps. You can't put thin wires like this to transport electricity. Okay, this one, but even a current of 20 amperes, this cannot tolerate. This will burn. This wire will burn out. So if you want to transport 1,000 amperes or something like that, you need really strong cables, thick cables. You must have seen those cables when they unroll it. Have you seen them on the roadsides and all that? You must have seen a huge wheel with those cables in, and they just unroll it and then lay it down and all that stuff. So it's a huge cable and expensive. But then, if you want to send electricity from here to one house, let's talk about just one house. So we have electricity here. All right, we want to help them. Fine. So you have 120 volts over here. And then you want to help them. So if I use wires and take it all the way there to that one house, if you want to send electricity to that house, and so you want 120 volts, you want 120 volts over there, and because they are operating some, they need some electricity. So let's say they need 3,600 watts, not too much. 3,600 watts is, we use much more than that, much more than that. Like for example, one hot plate is like 1,500 watts. Yeah. So if you're going to use 2 or 3 of them, you're already crossed. What about the other stuff you have in your house? The air conditioning system or heating systems or anything else, in the house, refrigerators. All those will consume electricity. Anyway, just consider that, okay, 3,600 watts is what you're expecting. How much current should be coming here? 30 amperes. Power is voltage times current. You can see 30 amperes required to flow here, which means 30 amperes are expected to go out from here. Correct? Now, let's say the wires all together, I'm talking about 50 miles. Okay? So all these wires together, even if you use thick wires, all this together, let's say it has 2 ohms resistance. 2 ohms all the way. So if it is 2 ohms resistance at the rate of 30 amperes, how many volts will be dropped in the wire itself? 60, right? 30 times 2, V equal to IR. V equal to IR, 30 times 2, 60 volts are completely lost in the wires. Out of what? Out of 120 volts. So what are you going to get over here? 60, which is not good enough to do anything. I mean, it can't turn these lights on. It can't turn on the TV because 60 is too less. 60 won't even give you a shock. You can touch 60 and still feel fine. You know, so 60 volts is not going to do anything at all. So all the appliances are not going to work efficiently. There's a lot of loss. Now 3,600 watts is what you want over there, but it's not going to go to 3,600. Let's see, look at the wattage. If this one is genuinely sending 3,600 watts, how much is the loss of power on the way? Loss of power. Power is I square R. How much is the loss of power? 30 square times 2. 1,800 watts lost out of 3,600. So you're only getting 1,800 watts of usage over there, which is not an efficient way of transferring energy, correct? So who's the main culprit over here? Culprit is the current. You can see that I square. That makes it all bad. I square, because whatever is the current, it's getting squared. And that's the main problem. So what is actually done then? What is done is this. Instead of sending it straight away there, this is 120 volts, we install a transformer right there. We install a transformer, and we install a transformer which can increase. This is step up. Increase the voltage 20 times. Increase the voltage 20 times, or 30 times. Let's say 30 times. So if the voltage is increased 30 times, from here to here, how many volts is going to be here? 36,000 volts. Is that right? 3,600. 20 times.
3,600.
Okay, I need 36,000. So it has to be 300 times then. So 300 times, that means what? That means the number of turns over here is 300 times bigger than the number of turns here. Do you get it? So if it is 1,000 turns here, it's 300,000 turns there. So what's happening is 120 here goes to 36,000 volts. This is high tension. But the 30 ampere over here also is going to be affected. What's the current over here now? What's the current here? Okay, the voltage jumped up to 36,000. What's the new current? 0.1 ampere. The current is only 0.1 ampere in these wires. And that's what you are taking all the way to the other end. 0.1 amperes going all the way. It's all 36,000, okay? So it goes all the way. And I cannot supply it straight to the house because they need only 120. So what do you need here? Step down. And the step down transformer simply works just the opposite of what you did over there. So it's going to be 300:1 ratio of the number of turns, 300:1. So the 36,000 volts will be stepped down to 120 volts. And the current of 0.1 amperes will literally be changed to 30 amperes for the house to use. Now let's look at losses. How many volts is lost through the wires? How many volts? The current is 0.1 amperes flowing through 2 ohms.
0.02.
So the voltage loss is 0.2 volts out of what? 36,000. You're losing 0.2 volts out of 36,000. There's nothing. There's nothing. It's not like 60 volts lost out of 120, right? Now this is only 0.2 volts lost out of 36,000. So it's nothing at all. That is not a big loss. What about power loss? Power is equal to I square R. I is 0.1. 0.1 square is 0.01. So it's basically 0.02 watts out of what? Out of 3,600 watts. Because this is power is exactly the same. Multiply this and this, you get the same power. You get it? Power is transformed, so power is not going to be different. So power is 3,600. Out of that, 0.02 watts you're going to lose because of the heating in these wires, which is negligible. So when you go to this point, you still have the 36,000, literally 36,000 volts there. The loss is 0.2 volts, is nothing at all. And the current, 0.1 amperes. So when you transform it, you still have 120 as the output. So this is exactly what we call as high tension transmission. So the benefit of this is you can use a wire that is thick, much thinner. You don't require a wire of this kind also. You can use thin wires and still achieve it. Can this take 0.1 ampere? Yeah. This can easily take 0.1 ampere, 100 milliamperes is nothing. This can take it. So we can actually transport electricity through these wires all the way to the other side. Less cost, less of everything. Of course, you need the transformers. Now, for the house, the transformer, yeah, it won't be that big. So you understand how the transmission is taken. So LG&E is producing electricity somewhere. Can anyone tell me at what speed is that generator spinning? At LG&E's generator? What is the frequency of the spinning action there? You know it. It is 60 times per second, 60 hertz. It is spinning 60 times per second, and that is basically the frequency that we all follow here. In some European countries, it's 50 hertz, like India also 50 hertz. So the generator spins at a different frequency, and the voltage output is also kind of different. It is 220, 240 volts, yeah.
This is why like touching down power lines is supposed to be so dangerous because it's got so many volts coursing.
Yeah. Yeah, the example I gave is 36,000 is, in fact, it's a lower one. Normally it will be like, 100 kilovolts. Yeah, it will be, if you read if you're on the tower, you've seen those posts, you've seen those posts like that with these wires like dangling like that. As you drive on a highway, you can see on the sides and all that. What is this? This is a high tension wire, high voltage. And if you go and see what is written there, they'll say warning, high voltages, and it'll say 100 kV, 100 kilovolts, 100,000 volts. So that is not a joke. Okay? So that's why if that power line kind of breaks off and then falls, then that can be really dangerous down there. So these are the high tension cables. And have you seen their thickness? They're thin. Of course, not as thin as this, because you're talking about serving power for an entire area. It's not like to one full area. So the transformers are very essential so distribution actually takes place after the transformer. So the electricity that is coming into the school, the wires are thick, but immediately there is a transformer very close to us, somewhere here or there. There is a transformer, and that transformer is the one which is the distribution center. So the thick wires need not be going a long distance. It's like a shorter distance. Thick wires are not going to be, these are the thick wires. These are the thin wires. In fact, the high tension cables are not even as thick as this. It's like thin. You can see how thin they are. They are thin but very strong in terms of, there's a steel inside with copper braided and then steel braided and a lot of braided wires. Because in the storm and all that, it can actually move and you don't want it to break. So it is made in such a way that it can take a lot of bending and swinging and all that, but still it should not break. Yeah. So that is high tension transmission, and there are transformers. You can actually see. You must have seen those transformers on the way, different places. You know, it is a place which is kind of guarded. You know, they'll be putting a fence around it, and this transformer will have kind of pipes going like that. You can look it up and see, and then maybe you'll find a cylinder on the top like that. So can you pull up power substation, transformer substation, and you'll see it. The main part of a loudspeaker is the magnet itself. So the magnet is a cylindrical sort of magnet like this. That is a kind of magnet. That is a magnet. And can you see there's a slot here? There's a slot. Into the slot goes a coil, like that. Into this slot goes a coil, perfectly fitting in. And this coil has turns, and this actually goes and fits in. And these turns, there are two wires that are taken out from there, and once this fits in, those wires actually are pulled out from there, and the diaphragm is attached to this cone, like that. The diaphragm goes there. And once everything is assembled inside, this diaphragm is secured by a springy material to hold it in place. Now, what exactly happens when you pass electricity? Now these are wires carrying current in a magnetic field, right? So when the wires carry current in the magnetic field is like perpendicular. It's a cylindrical magnet. Like the central part, and there is a, so in the space there is magnetic field going one way. So when a current passes through the wire and a magnetic field is perpendicular, there's a force. So when a current is, say, for example, flowing down, and the magnetic field is that way, then the force is that way. So the whole coil goes in. You get it? And when the current direction is reversed, it goes out. So the alternating current is put in, it moves back and forth. So if I'm speaking with a certain frequency, this will move with the same frequency. So it generates sound. Makes sense? So a loudspeaker works on force on a current carrying conductor placed in a magnetic field, that concept. Now a motor is a moving coil. So you saw this also has a moving coil. But there's a difference between this and the motor. In a motor, we want it to spin continuously. This is not going to spin continuously. The coil is like that. When you pass electricity, it spins against a spring. There's a spring holding it in place. If there's no spring, if there's no spring holding it, it will just kind of spin all the way that way, and then the torque will reverse. So it will keep oscillating like that. It won't spin continuously in one direction, because when it is like this, there is a torque to turn it that way. But once it flips the direction, so this way, it goes like that. Once it goes like that, now the force is going to be the opposite. So it will turn like this, and like this, and like this. So if I'm going to send a current, it is going to move that way, but it won't stay there. It has to come back. So it will keep oscillating until it comes to the center. It keeps fluctuating like that till it comes. So we don't want it to fluctuate. We want to continue to move. How can you make it continuously move? That's by using brushes, right? Those are the brushes. And that is the coil that is moving continuously, which means there is no physical wire connecting that coil and the outside. There's no physical wire. Because if you have a physical wire, what will happen to the wire? Get twisted. So you don't want that. You want it to be free. You can't have a wire connecting to it like those bumper cars. The bumper cars. Have you seen the bumper cars? They're powered externally. There's no battery inside. There's externally powered. Where's the power coming from? From the mesh on the top. So the voltage is applied to the entire mesh, and there is a antenna looking stuff. There's something that rubs on it like that. So this is the pole. There's something that rubs on that metal mesh, and because it is rubbing on it, it is picking up the voltage from there. And where is the other terminal? The floor. Have you noticed the floor is different material? It's metal. The floor is metallic, and the wheels are conducting. So the current is actually flowing from here into the motor and goes down. So they can turn off the whole thing, and all the cars will stop wherever they are. Right? All the cars will stop wherever they are, because it is not something, once they don't have power, then, well, they can roll, but it is not going to be powered. So they use these brushes. This is kind of brush action. And that's the same thing that we need to do for a motor. So here is a motor, a simplified diagram of a motor. So that's a magnet. The simplest motor thing. So that's a coil that is supposed to be spinning, but you don't want it to, you want the spinning to be always in one direction, right? So we use what is known as a commutator. It's like two D's, you notice it. It's like this, two D's. You see it? It's like two D's, and so the whole thing spins. Now, where are the brushes? There's a carbon brush sitting here under spring action. There's another carbon brush touching on this side, again under spring action. And those two carbon brushes, you can actually probably see the carbon brushes through here. There's a carbon brush and there's another carbon brush. So the carbon brushes are going to just rub on it. And this carbon brush is what brings out the output. All right, now let's see how it works. If this is north, that is south, and we wanted to use as a motor, right? So let's connect it to a power. If I connect it to a power, the current is going to flow this way. The current goes through the brush into this. These are split rings. The current goes here, and then it goes here. Now, when the current goes in that direction, which way is the magnetic? Which way is the force? Which way is the force? Which way is the magnetic field? Don't use the right hand, left hand. Fleming's left hand rule. Because I need the force, because I already have the current. This is not induced. Only for induced current, pick up your right hand. Okay? Magnetic field is that way. So my pointing finger is that way. Current is into the board. Current is into the board. So it's going to move down. What about this current? It's coming back. Hence it's going to move up. So this is going to move down. That's going to move up. So it's already causing a spin. Okay? So after spinning like that, what will happen now? The commutators have changed positions from this position. Now they are in this position. There's a gap here, there's a gap here. Now the brushes are actually going to be touching the gaps. But then because of the momentum that the coil already got, it will flip. So the A, B becomes BA after some time. So the coil actually goes like that. This is B and that is A. So what's happening now in B, the current is going to be pushed that way in B. And so the force is still downward. Make sense? The current was actually coming backwards when the coil was in that position. But when the coil switched its positions, the current in A is going to be inward, and the current in B, outward, and the current in B is going to be inwards. So counterclockwise torque is still applied. So this coil AB becomes BA, and becomes AB and BA, and it should keep going. It should keep going. That is a motor. and then you can use it for a purpose. That's what I was trying to demonstrate from here. See the two carbon, not carbon, this is copper. The copper brushes, and you can see the commutator there. I'll pass this along. You can actually see this is called this is a split ring or commutator. Commutator because when the spring commutes, contacts are always established wherever the thing is. So I can just pass this along. You just kind of turn it around and you can see how the split rings are used. Split rings are used. Okay. So the coil will continuously turn. Now, when the coil becomes vertical, what is the torque? When this coil becomes vertical, there's no torque because no current, because the brush is not touching anywhere, right? No current. And even if there's current, the coil is like this, vertical, so the pull is going to be like in the same direction, so no torque. So what will be the end result of this movement? The movement will be like jerky. So it will be like going from here. When it's here, it doesn't have any power to go. So it's like it goes fast from here, and then fast from here, and fast. Like it will be like jerky movements, like not continuous. It's like fast. But when it's done faster, you don't see the difference. But it is definitely not a smooth run. If you want a smooth run, what you need to do is just don't depend on one coil. Put many coils. Put many coils slightly off from each other. And that is how it is constructed here. And I'm going to pass this. So you can see instead of just a split ring, it is multiple splits. Instead of just two pieces, it will be like this. So it's basically like that. Make sense? Now, what you see over here, they are separations. This is separation. So the one winding is going from here. One winding goes from here and then goes around and comes back. And the other winding will start from here. And the other one winding starts from here. So there are many, many, many loops going in all directions. And that's what makes it smooth.